This is lecture number 37 of our course on fundamentals of transport processes, and we were discussing a general convection diffusion equation for the concentration or temperature field. So, the equation has the general form dc by dt plus the divergence of velocity times the concentration is equal to d times the Laplacian of the concentration plus any source or sink of mass or energy within the system. And when you scale the length scale by a characteristic length L and the velocity by a characteristic velocity u, you get an equation of the form shown here, where you have a Peclet number times the time derivative and the convective term on the left is equal to the Laplacian of the concentration field plus the source or sink of energy or mass, where the Peclet number is u times L by d. U is the characteristic velocity, L is the length, and d is the diffusion coefficient. First, we looked at strategies for solving the limit where the Peclet number is small compared to 1. In that case, we are solving d del square c plus s is equal to 0. And we looked at various ways of doing that. It's basically ways of solving the Laplace equation. We did it first by separation of variables in Cartesian coordinates, in cylindrical coordinates, as well as in spherical coordinates. And in particular, in spherical coordinates, we saw that the solutions have the form of spherical harmonic solutions. We also saw another way of solving the same equation using the framework of point source, a delta function source, and that gave us results for a relationship between the spherical harmonic expansion on the one side and the distribution of sources and sinks on the other side. So, those were the two strategies that we have looked at so far for solving this diffusion equation in the limit of Peclet number being small compared to 1. The diffusion dominated limit. Then we looked at the case where the Peclet number is large compared to 1, P is much greater than 1. And if you just look at this equation simplistically, one might think that all you need to do is to neglect the diffusion terms on the right hand side completely and just solve the equations for the convective part alone. Last class we looked at the simplest case, the flow past a flat plate, where I have a linear velocity in the flow past the flat plate. The velocity in the x direction, x is the flow direction, the streamwise direction, y is the cross stream direction, where there is a variation in velocity. And we assumed a linear velocity profile at the surface. U x is equal to gamma dot times y, where gamma dot is the strain rate. And at steady state, we were trying to solve the equation, the divergence of u times T is equal to the thermal diffusivity times the Laplacian of the temperature. The configuration was as follows. We have a fluid which is incident on this heated surface at a temperature T is equal to T naught. The surface is unheated up to x is equal to 0. Okay. So, there is a cold section of the surface up to x is equal to 0, which is at the same temperature T naught as the incoming fluid. And at x is equal to 0, the heated section starts, T is equal to T1, and it continues for some length L. And as I told you, this is a simple approximation for the flows in heat exchangers, for example, where as the fluid in the tube sides flows into the heat exchanger, initially it is at some cold temperature, and at the inlet of the heat exchanger there begins a heated section and it continues downstream. So, that was the configuration that we were trying to solve for in the high Peclet number limit. In this particular case, the velocity itself is not specified. What is specified is the velocity gradient gamma dot. This velocity gradient has dimensions of 1 over time. The only length scale in the problem is capital L, the length of the plate, and therefore, I can define the Peclet number as gamma dot times L square by alpha. Okay. Note also that u x is independent of x, it is a fully developed flow, and u y is equal to 0 everywhere. So, the flow is only in one direction. When we put this into the conservation equation, okay, we got an equation of this form. And if we scale x and y by L, which is the only length scale in the problem, we get a scaled equation with a Peclet number in it, as expected, okay, with the scaled equation with the Peclet number in it. And if we just simplistically neglect diffusion, we just get that dt by dx is equal to 0, and the only solution of that is t is equal to 0 everywhere within the flow. Of course, that does not satisfy the boundary condition that T star has to be equal to 1 on the plate surface itself. And I had explained to you why mathematically that there was this contradiction. When we neglected the diffusion terms contain the highest derivative. They contain the second derivative with respect to the y coordinate. And therefore, we have two boundary conditions which can be satisfied in general. However, when we neglect the diffusion terms, we are neglecting the highest derivative, and therefore, we end up with an ordinary equation in the y coordinate, which does not contain any boundary conditions. And because of this, we are unable to satisfy boundary conditions. Physically, the reason that we are not able to satisfy boundary conditions is because the flow is parallel to the surface, it is tangential to the surface. At the surface itself, there is no velocity perpendicular to the surface. Convection can transport mass, momentum, energy only in the direction of flow. Since there is no flow perpendicular to the surface, there is no convective transport perpendicular to the surface. Therefore, the only way that heat can be transported from the surface to the fluid is due to diffusion, due to the molecular motion of the molecules. We have neglected that diffusion term in this case, and therefore, we are not able to satisfy boundary conditions. Since we have neglected diffusion, there is no way for heat to be transferred from the surface to the fluid, and because of that, we are not getting heating anywhere within the fluid. So, what is the resolution of this problem? As I told you, when we scaled the x and y coordinates by L, we assumed that capital L was the length scale for the variation of the temperature field. However, we are looking at a situation where there is convection, rapid convection along the flow direction, and there is the diffusive effect is small. So, you would expect the flow to sweep any heat that is transported from the surface to sweep that downstream, and physically one might expect the effect of the plate to be restricted to a thin layer near the surface. Diffusion is present nevertheless, and therefore, one cannot have discontinuity in the temperature, but that diffusion effect is small compared to convection over length scales comparable to the length L. And because of this, we would expect convection, the heating due to the plate to be restricted to a thin layer near the surface. If the temperature, the length scale for the variation of the temperature field is small compared to capital L, then the gradients are large, and because the diffusion term has the second derivative with respect to y, if the length scale is small, the derivative is large, and one could still have a balance between convection and diffusion. How does one decide what is the length scale? We postulate a length scale, put it into the equation and see what it has to be in order that convection and diffusion are of the same magnitude even as the Peclet number goes to infinity. So, that is the strategy that we followed in the last lecture. So, we postulated a length scale small l such that the effect of diffusion is felt only within that length scale near the surface. So, we scaled x by capital L, which is the total length of the plate, because that is the length scale over which there is variation in the x direction, and we scaled y by small l, which is the smaller scale over which there is a balance between convection and diffusion. And we put that into the conservation equation. And finally, we found that this dimensionless group had to be finite in the limit as Peclet number goes to infinity if convection and diffusion are to continue to be of the same magnitude even as Peclet number goes to infinity. So, if the convection and diffusion are to be comparable even as the Peclet number goes to infinity, Peclet number based upon the length scale L, which is the length of the plate. Okay. If convection and diffusion are to be of the same magnitude, then we require that this thing has to be order 1, or small l by capital L has to go as p e power minus 1/3. Okay. So, as Peclet number becomes larger and larger, this boundary layer length scale small l becomes smaller and smaller, and it decreases as p e power minus 1/3 as the length scale becomes large. So, that gave us a scaling for the boundary layer thickness. For a plate of length capital L, the microscopic length, the boundary layer thickness has to go as p e power minus 1/3 times capital L. But how do we proceed and actually solve the problem? We still have in this case a second order differential equation in the y coordinate and a first order in the x coordinate. So, it is a second order partial differential equation, second order in y and first order in x. So, how do we solve this? The solution was based upon a little bit of physical insight. Okay. At any given location x, okay, at a given location x, there is convection, there is diffusion from the surface, and there is convection downstream, okay, from that location. Okay. Therefore, the temperature field at that location should depend only upon the distance x from the upstream end of the heated section and not on the total length L. I have neglected in this case streamwise diffusion. Therefore, whether the plate is of length L or of length 2L, that is downstream of the location x, and therefore, the boundary layer thickness, the temperature at that location cannot depend upon the total length L of the heated section. Okay. It should only depend upon the distance x from the beginning of the heated section. Okay. So, rather than writing small l by capital L is equal to P e based upon L to the minus 1/3, what I said based upon physical insight was that at a given location x, the boundary layer thickness can depend only upon the distance x itself. In that case, the only form for the relation is of this type. Okay. Small l by x is equal to P e based upon x to the minus 1/3 power, where the Peclet number based upon x is gamma dot x square by alpha. You substitute x instead of L. So, now x is the downstream distance, the coordinate along the streamwise direction, and since the boundary layer thickness depends only upon x, it already depends upon x. When I express the equation in terms of the scaled coordinates, okay, which is y divided by the boundary layer thickness, then I should end up with an equation which depends upon this similarity variable alone. Okay. It should not depend individually on x and y, and it should also not depend upon the strain rate or the diffusion coefficient. It should depend only upon x alone. I am sorry, it should depend only upon eta alone. So, this was the similarity variable that we had defined, okay, based upon our argument that at a given location x, the temperature field depends only upon x. So, this was inserted into the conservation equation, okay, using chain rule for differentiation, and as expected we did in fact end up with an equation which depends only upon the similarity variable eta alone. Okay. It does not depend individually on x and y, but it depends only upon the similarity variable eta alone. And this is a second order differential equation in eta. We have to prescribe boundary conditions for this. Those boundary conditions emerge from the initial boundary conditions that we had for the x coordinate. At y is equal to 0, t star is equal to 1 implies that at eta equal to 0, t star is equal to 1. As y goes to infinity or as eta goes to infinity, t star is equal to 0. And at x is equal to 0 for all y greater than 0, t star is equal to 0. X is equal to 0, finite y implies that eta goes to infinity. As I showed you in the last lecture, these two boundary conditions, one in the y coordinate and the other in the x coordinate, reduce to the same condition when expressed in terms of eta. That is consistent because I had reduced an initial first order equation in x and a second order equation in y to just a second order equation in eta. The original equation had two conditions in x and two conditions in y and one in x, and whereas the equation that results in terms of the similarity variable can have only two conditions, and these were the two conditions. We had solved this equation explicitly and got the temperature field. Okay. The next task is to get the heat flux. Okay. I told you that the heat flux is equal to minus k dt by dy at y is equal to 0. That is, the flux that is emerging from the surface is equal to minus k times dt by dy at y is equal to 0. I can express that in terms of eta, because y is related to eta as eta is equal to y by the boundary layer thickness. So, I can express that in terms of eta. Okay. And once I do that, I get an expression for the heat flux at the surface, okay, which goes as x power minus 1/3. So, the heat flux at the surface decreases as you go downstream. That is because the boundary layer thickness is increasing. The flux goes as the temperature difference divided by a length scale. In this particular case, that length scale is the boundary layer thickness. As the boundary layer thickness increases, the heat flux is going to decrease. What is the total heat coming out of the surface? Okay. I should change this. This is actually okay, because I have So, what is the total heat flux coming out of the surface? This is the total amount of heat coming out per unit length perpendicular to the plane. Okay. because as you recall, in this case we are considering a two-dimensional problem, okay, where there is a plane surface and the fluid is incident on that surface, and this is a two-dimensional problem. Therefore, we are considering a two-dimensional problem per unit length in the third direction perpendicular to the plane of the board. Okay. So, the total amount of heat coming out per unit length perpendicular to the plane is going to be equal to integral 0 to L dx q y. Okay. That is, you integrate the heat coming out per unit area in at each differential area along the x direction, and then add them all up. Okay. So, this is equal to the total heat that is coming out. Okay. This is equal to k into T 1 minus T naught. Integral 0 to L dx by x power 1/3. Okay. Because I have this dependence on x in the equation for the heat flux. Okay. So, this is equal to k into T 1 minus T naught by alpha by gamma dot power 1/3 into 3 power 2 by 3 by gamma 4 by 3 into 3 by 2 times L power 2 by 3. Okay. So, this is equal to 3 power 5/3 by 2 gamma of 1 by 3 into k T 1 minus T naught by alpha by gamma dot L square power 1/3. Okay, so, this is the final equation for the heat transfer from a plate. Okay. And the Nusselt number traditionally is defined as 2 q by k into T 1 minus T naught. Okay. And you can see that this would be given by 3 power 5/3 by gamma of 1/3 into Peclet number based upon L to the minus 1/3 power. Okay, I am sorry, this is Peclet number based upon L to the plus 1/3 power. Yeah. So, this gives us the Nusselt number versus Peclet number correlation for the heat transfer from a flat plate. When I discussed this initially, when we looked at correlations for different situations, I told you that the Nusselt number goes as Peclet number to the 1/3 power. This is basically 3 power 5/3 by gamma of 1/3 Re per 1/3 Prandtl number per 1/3, because Peclet number is the product of the Reynolds number and the Prandtl number. So, this is the correlation for the heat transfer from a flat plate. Okay. In the limit where the flow is laminar, so that the velocity is linear at the surface. In that case, the correlation for heat transfer goes as a constant times Peclet number to the 1/3 power. And the reason it goes as Peclet number to the 1/3 power is physically is because the heat flux from the surface goes as the temperature difference divided by a length scale. That length scale goes as P power minus 1/3 from the scalings that we had just derived. Therefore, the Nusselt number will go as P power plus 1/3 as expected. Okay. This we solved for the particular case where the velocity is linear. Okay, there is a linear velocity profile, where there is a linear velocity profile at the surface. However, the solution is actually more general than that. Okay. Regardless of the velocity profile that I have, okay, the boundary layer thickness is actually small compared to the length scale. Okay. So, for the solution to be valid, the only requirement is that the velocity profile has to be linear over a length scale comparable to the boundary layer thickness. Okay. The velocity profile has to be linear over a length scale comparable to the boundary layer thickness. So long as the boundary layer thickness is small compared to the macro scale, the velocity has to come down to 0 at the surface anyway. So, near the surface the velocity has to increase linearly from 0, and if you are expanding in a thin region in a Taylor series expansion, the first term in that expansion will be the linear term. Okay. So, this will be the first term in the expansion for any velocity profile, provided the region over which I am expanding is thin, small compared to the macroscopic scale. In that case, the velocity profile near the surface is going to be linear anyway, and therefore, I can use an expansion in this velocity profile of this form, u x is equal to gamma dot y at the surface. This is valid whenever there is a no slip condition at the surface, so that the fluid velocity has to come down to 0 at the surface. It is not valid in general if you had a non-zero velocity at the surface. We will see a little later how to deal with non-zero velocities at the surface. Okay. So, this is the Nusselt number correlation for this simple case of the flow past a flat plate. Let us now consider a more complicated case, heat transfer from a spherical particle. Okay. So, this is a case that is actually of practical interest. Okay. One might very often have situations where there is transport from a spherical particle or some other shaped particle within the flow. So, first I will consider the case where there is heat transfer from a spherical particle, and then we will look at some general results that can be obtained for any shape of particle. Okay. So, we have a particle of radius r, okay, which is at temperature T naught, okay, and there is fluid flow around the particle. And far upstream the fluid has some velocity u. Okay. The fluid velocity is u far upstream of the particle. Okay. The temperature far away from the particle is T infinity, and one would like to know what is the heat flux due to the flow as well as diffusion, thermal diffusion from the particle. Let us fix our coordinate system. We have a spherical particle, and therefore, it is most convenient to consider a spherical coordinate system. This spherical coordinate system has an axis of symmetry. Okay. That is, as you rotate around this axis, there is no change in the velocity fields. So, it is most convenient to consider this as the z axis, and the angle theta is measured from this z axis, while r is the distance from the origin in this coordinate system. Okay. And in this coordinate system, I will prescribe u r, u theta, and so on. Okay. We assume that the flow is viscous in the low Reynolds number limit. Okay. And in that case, you can get analytical results for u r and u theta. We will not derive it here. I will just use these results to calculate the heat flux. Okay. The analytical results are u r is equal to u cos theta 1 minus 3 r by 2 r plus r cubed by 2 r cubed, okay, and u theta is equal to minus u sin theta So, these are the expressions for the velocity field, okay, everywhere within the flow. U phi is equal to 0 because there is no flow in that direction, and there is no dependence of either the velocity or the temperature on the phi coordinate, which represents rotation around the z axis. Okay. So, this is heated sphere at temperature T naught in a fluid at temperatures equal to T infinity. Okay. So, I can define my scale temperature as usual, T star is equal to T minus T infinity by T naught minus T infinity. Okay. And I will define scaled radius as r by capital R and u star so, scaling by the obvious scales, the velocity scale is u, the radial distance is capital R, and T is scaled as T minus T infinity by T naught minus T infinity. So, the boundary conditions are at R star is equal to 1, T star is equal to 1, and as R star goes to infinity. Okay, so, the temperature is 1 at the surface and it goes to 0 as the distance goes to infinity. Okay. And the scaled velocities expressed in this form are u r star is equal to cos theta 1 minus 3 by 2 r star plus 1 by 2 r star cubed, and u theta star is equal to minus sin theta 1 minus 3 by 4 r star minus 1 by 4 r star cubed. And if you insert these into the steady state convection diffusion equation, u dot grad is equal to alpha del square T. Okay. What you will get is u r partial T by partial r plus u theta by r partial T by partial theta into the Peclet number is equal to 1 by r square d by dr of r square dt by dr plus 1 by r square sin theta d by d theta of sin theta. Okay. So, this will end up being the scaled equation. I just scale the velocity by capital U, the length by capital R, okay, and the Peclet number is equal to u r by alpha. Okay. Now, in this equation, if we take the limit Peclet number becoming large compared to 1, the equation just becomes u r dt by dr plus u theta by r dt by d theta is equal to 0. Okay. One can also write this alternatively as u dot grad T is equal to 0. Okay. So, what this says is that u dot grad T is equal to 0, that means that the gradient of T along the velocity is equal to 0. Temperature does not vary along streamlines. Okay. Temperature does not vary along streamlines, the temperature at the upstream entrance is equal to T infinity. Therefore, if the temperature upstream is T infinity and it does not vary along streamlines, then the temperature has to be T infinity everywhere. Okay. So, that is the only solution that you can get. The temperature has to be T infinity everywhere. It cannot satisfy this boundary condition. In order to satisfy this boundary condition, as in the problem of the flow past a flat plate, we have to postulate a boundary layer of thickness small compared to r at the surface. Okay. Previously, we had scaled r by capital R. The assumption there was that the length scale for the variation of the temperature field is capital R itself. Okay. But when the length scale is capital R, the Peclet number is large and diffusion is small compared to convection. Okay. Diffusion and convection can be of the same magnitude only if there is a smaller length scale which is small compared to capital R, such that the temperature field varies only over that small length scale. In that case, the gradients of the temperature field are large and one could have a balance between convection and diffusion. So, what we have to do now is to postulate the presence of a layer near the surface. Okay. The presence of a layer near the surface where there is the effect of heating from the sphere is penetrates into the fluid. What should be this distance, the length scale? We will obtain that from the consideration that convection and diffusion are of equal magnitude within this layer. Okay. So, the surface of the sphere itself is at r star is equal to 1. Okay. Therefore, I will postulate that there is another coordinate, okay, r star is equal to 1 plus delta y, okay, where y is a scale distance, okay, within the fluid away from the surface. It is basically delta times y is the distance of a point from the surface, because r star is equal to 1 is the surface. So, r star is equal to 1 plus delta y gives you basically the distance of a point in the fluid from the surface of the sphere, and that distance has to be small for there to be a balance between convection and diffusion. Okay. So, this y is the variable that I am using. Okay. Y is the scaled variable that I will use for differentiation, and delta is a boundary layer thickness. Okay. Y I will assume is order 1. Okay. It remains finite in the limit as Peclet number becomes large. Delta becomes smaller and smaller as Peclet number becomes larger and larger, in such a way that delta times y gives me a region near the surface of the sphere where there is a balance between convection and diffusion. Okay. So, it is important to note that I will assume that y is a scaled coordinate which continues to be order 1. It varies from the temperature, the effect of heating from the sphere is non-zero when y is of order 1. Delta is a length scale that is going to go to 0 as the Peclet number becomes large. Okay. So, y is a scaled coordinate in our case. So, first of all, I have to substitute this in the equations for the velocity field. Since I am interested in the region near the surface, it will be sufficient for me to find out approximate expressions for the velocities in the region very close to the surface. Okay. It will be sufficient to find out approximate velocities in the region very close to the surface. Okay. So, my velocity field u r was equal to cos theta minus 3 by 2 r plus 1 by 2 r cubed. Okay. I substitute for r in terms of 1 plus delta y. Okay. So, this becomes cos theta 1 minus 3 by 2 into 1 plus delta y plus 1 by 2 y whole cubed. Okay. Now, I can use a binomial expansion in this small parameter delta. Okay. So, this is going to be equal to cos theta 1 minus 3 by 2 into 1 plus delta y power minus 1 plus 1 by 2. Okay. And if I expand this out, I will get cos theta 1 minus three by 2 plus 3 by 2 delta y, okay, minus 3 by 2 delta y the whole square plus 1 by 2 minus 3 by 2 delta y. Okay. And plus 3 delta y the whole square, okay, using a binomial expansion. Okay. And you can see that in this the leading order terms actually cancel out. I have 1 minus 3 by 2 plus 1 by 2, those 3 cancel out. Okay. The terms proportional to delta also cancel out. I have 3 by 2 delta y minus 3 by 2 delta y, and the first correction that I get is of order delta y the whole square. Okay. So, this in this limit is approximately equal to cos theta times 3 by 2 delta square y square. Okay. So, the radial velocity goes as delta square times y square very near the surface. Okay. What happens to the other velocity u theta? Okay. U theta is equal to sin theta, okay, to 1 minus 3 by 4 r minus 1 by 4 r cubed. Okay. This can once again be expanded out, sin theta into 1 minus 3 by 4 1 plus delta y minus 1 by 4 into 1 plus delta y the whole cubed. And if I use a binomial series, I will get 1 minus 3 by 4 minus 3 by 4 minus okay, plus 3 by 4 delta y minus 1 by 4 plus 3 by 4 delta y. In this case, the terms that are order 1 actually cancel out, 1 minus 3 by 4 minus 1 by 4. Okay. And what I end up with is equal to minus sin theta into 3 by 2 delta y. Okay. So, these are the velocities u r and u theta. The approximations for the velocities very close to the surface when delta is small compared to 1. Okay. So, these are the approximations for the velocity fields. The radial velocity goes as delta square, the velocity in the theta direction goes as delta. Okay. There is no surprise, because at y is equal to 0 itself, both components of the velocity have to be equal to 0. So, I now put this into my differential equation, P e into So, this is the differential equation. and I substitute in terms of r in this equation and also substitute the velocities that I got. Okay. So, I put this in and I will get P e into 3 by 2 delta square y square cos theta, okay, into partial t by partial r is 1 over delta partial t by partial y, okay, plus u theta is minus 3 by 2 delta y sin theta by 1 plus delta y, r is 1 plus delta y times partial t by partial theta. Okay. On the right hand side, I have 1 by 1 plus delta y the whole square. D by dr is 1 by delta d by dy of r square is 1 plus delta y the whole square times 1 by delta partial t by partial y plus 1 by 1 plus delta y the whole square sin theta d by d theta of sin theta dt by d theta. Okay. Now, delta is small compared to 1. Therefore, I can neglect delta in comparison to 1 here, here and here as well as here. Okay. I can neglect delta in comparison to 1. Okay. And once I do that, I get P e into 3 by 2 delta square y square, I am sorry, delta y square cos theta partial t by partial y minus delta y sin theta partial t by partial theta. The first term here is 1 by delta square partial square t by partial y square. Okay. And the second term is 1 by sin theta d by d theta of sin theta partial t by partial theta, after I have neglected all the terms proportional to delta, retaining only the leading order terms. Now, in this equation, it is easy to see this first term goes as order 1 over delta square, whereas the second term does not contain any deltas. In the limit as delta goes to 0, this second term is small compared to the first, okay, because we expect delta to become a small number. Therefore, 1 by delta square will become a large number. Therefore, in the limit as delta goes to 0, you would expect this to be small compared to the first term. On the left hand side, of course, both terms are proportional to delta. Okay, so, both of them are of equal magnitude in the limit as delta goes to 0. Okay. So, if I neglect the second term and multiply throughout by delta square, okay, what I will get is P e delta square into 3 by 2 to y square cos theta partial t by partial y minus y sin theta partial t by partial theta is equal to partial square t by partial y square. Note that at the surface of the sphere, the flow at the surface of the sphere is in the theta direction. So, theta is the streamwise direction, r is the cross stream direction. Okay. R is the direction perpendicular to the flow at the surface of the sphere. Okay. And as in the case of a flat plate, what we are finding is that the diffusion in the cross stream direction, the first term there, is large compared to the diffusion in the flow direction, in the theta direction along the surface. So, diffusion perpendicular to the surface is large compared to diffusion along the surface when the boundary layer thickness is small. So, that is consistent with what we had in the flow past a flat plate. What is different here in the flow past a flat plate is that we have convection both in the r and theta directions, and both of these are of equal magnitude. Okay. Okay. So, as I said, within the boundary layer y is order 1, delta goes to 0. In the limit as delta goes to 0, if y is finite, this number has to be order 1 if there is to be a balance between convection and diffusion. And once again we get delta is equal to P e power minus 1 by 3. Okay. So, when delta is equal to minus P e power 1 by 3, we have a balance between convection and diffusion in the limit as the Peclet number goes to infinity. Okay. So, this provides us with the boundary layer thickness. As in the case of a flat plate, the boundary layer thickness goes as the Peclet number to the minus 1/3 power. Once again, no surprise. Very close to the surface, if we can approximate the velocity profile as the linear function away from the surface, then the velocity increases proportional to the cross stream distance. The diffusion coefficient goes as 1 over that length scale square. So, ultimately I will get P times the L cubed being order 1. Okay. So, in that sense it is no longer a surprise. So, if we use delta is equal to P e power minus 1/3, then our equation becomes 3 by 2 into y square cos theta partial t by partial y minus y sin theta partial t by partial theta is equal to partial square t by partial y square. So, this is a partial differential equation, contains two variables, one is theta and the other is y. In the previous case, we had only one component of the velocity. We assume that the similarity variable does exist. Assume a similarity variable of the form y by h of theta, where h is some function of theta. I will put this form of the similarity variable into the differential equation, solve it, and then try to see whether I can get the functional form of this similarity variable in such a way that the resulting equation does not depend individually on theta and y, but depends upon the similarity variable eta alone. Okay. So, instead of trying to use some physical insight as in the case of the flow past a flat plate, in order to derive what the similarity variable will be, I will go ahead and assume a form for that similarity variable. I will put that into the equations, and the resulting equation that I get, one can then check whether there is some form of this function h of theta which actually satisfies the condition that the resulting equation is a function of eta alone. Okay. So, this part we will continue in the next lecture. Okay. To briefly recap what we did in this lecture, first we looked at the flow past a flat plate, okay, and explained to you how to get a Nusselt number correlation. In this case, the heat transfer from the surface, there is a boundary layer of thickness Peclet number power minus 1/3 at the surface. Because the boundary layer thickness decreases as Peclet number to the minus 1/3 power, the heat flux, which is the temperature difference divided by that length scale, is proportional to the temperature difference divided by that length scale. There are some constants of course, but in the limit as the Peclet number becomes large, the heat flux has to be proportional to the difference in temperature divided by the boundary layer thickness. That heat flux goes as P e power plus 1/3 because the length scale is going as P e power minus 1/3. Okay. And once I use that condition, I can then derive an expression for the Nusselt number in terms of the Peclet number or the Reynolds number and Prandtl number. And then we looked at the heat transfer from a spherical surface. This was for a laminar flow. Okay. The convection diffusion equation for the laminar flow in the heat transfer past a spherical particle. the velocity components are prescribed for us in this case. We will see it is outside the scope of this course to derive these velocities themselves, but we will assume that these velocities are known, and once these velocities are known, we can then insert them into the convection diffusion equation. Okay. And of course, if you scale the radius by capital R and the Peclet number is large, then you end up with an equation of the form u dot grad T is equal to 0. That means the temperature does not change along streamlines, and therefore, whatever temperature is at the inlet continues to be there throughout the domain. With this, we cannot satisfy the boundary condition T star is equal to 1 on the surface of the sphere. In order to satisfy the boundary condition, we had postulated boundary layer thickness, and we had calculated the value of that boundary layer thickness. We have not yet done that the similarity solution for the temperature field. That we will continue in the next lecture. So, we will stop here, and I will briefly summarize this in the next lecture before we continue to determine what is the form of the similarity solution. So, we will see you then.